Juice was launched on the 14th of April 2023. The first phase, which is called launch and early orbit phase, went very smooth, and within less than 24 hours the spacecraft was safe and was operational, and it was ready to start to continue with the critical operation like switching on the payload. One of the first things that we had to do was to deploy the RIME antenna. The RIME antenna is a 16-meter long segmented dipole, and the purpose is when Juice would be on the Jovian system, the RIME antenna will measure the thickness of the ice of the moon, it will measure the depth of the ocean, and in general it will probe the inside of the moon, so a very important instrument. And we have to deploy this antenna as soon as possible after the launch to avoid that due to the cold in space, the mechanism, the deployment mechanism, the hinge of the segment of the antenna could freeze and therefore make the deployment very difficult or even impossible. So here we go. 3 days after launch, we give the command to deploy the antenna, and it didn't work. The deployment was partial with one segment, and the rest of the antenna was stuck. Of course, a lot of concern, big panic, because not deploying the antenna would have meant to lose the instrument, one of the most important instruments, and to lose the capability to look inside the moons. Well, there was a lot of trial error. Eventually, we managed to deploy the antenna, and it took 1 month. And that was done thanks to the commitment, ingenuity of a lot of people, engineers from ESA and from industry. So what will follow is a little bit of history of what's happened in this month, why the antenna was stuck as a first instance, and how people managed to deploy it. And the story is told by Ronan Le Letty, who was one of the key engineers, together with the industry, who allowed to transform a potential disaster in a success story. Enjoy it.
When I was first approached by Natalie to give a lecture on this topic, she asked me, it should be understood by everyone. This is a kind of challenge because sometimes in this story, the devil is in the details. So I will try to give some explanation to everyone. Sometimes it will be technical. I will also try to explain what the pin which was mentioned in Twitter, where it was and how it came in the game. So the presentation will be given in 5 sections. We will have first an introduction of the Juice mission and the spacecraft, and especially all the appendage on board Juice, and especially the RIME radar antenna. Then we will move to what is the RIME radar antenna, what is its deployment overview, and we will start to address the anomaly as well as the operational constraint after launch. Then the third part will be focusing on the root cause analysis. Then we will address the recovery, and we will be finishing with the lessons learned. Before we start and go to Juice, some additional word on myself. I've been working in the industry in SME for 20 years with several units delivered and flying, mostly starting from R&D to a flown product. So on the left side you can see a piezoelectric scanner, which was first developed in '94 and flown on Rosetta in 2004. And on the right side, a voice coil or Lorentz actuator, initially developed in 2007 and flown on board MTG with the scanner of MTG in 2022. So you see the time frame from first R&D to a launch, 10 years typically. Juice was an opportunity for me to have a more system view. My involvement in Juice was a technical support starting end of phase A till phase E1 and still continuing in the present phase E2. I was integrated at 80% of my time into the Juice team during 6.5 years. And I was in charge of several procurement for the Juice spacecraft, the solar array drive assembly, the RWI antenna, the long-wheel probe booms. After that, I gave some AIV support for the integration and test of all the appendage on board the spacecraft, also the spacecraft alignment. And finally, on-site ESOC in Darmstadt, I was part of the project support team, giving the support for all deployment. So from my initial technical background in industry is not directly related to the topic. Basically, I learned the topics in phase B1 of the project. First part, let's go back to the Juice missions and the spacecraft and the various appendage. Before we go to the topics of today is the in-flight anomaly. For appendage and related deployment, they are part of the commissioning of the spacecraft and they are all a single point of failure. So in average, because it's a single point of failure, because we cannot test easily such deployment on ground, we still have, in average, 2 failures per year all over the world. We are in contact with some NASA guys which are monitoring a database of the topics. And for instance, this spacecraft, Viasat 3.1, failed to deploy its large astromesh reflector from Northrop Grumman in July 23. They lost 90% of their link budget, which means they have lost around 350 millions of dollars. So it's tough topics. It can go wrong. Mechanisms can work, but needs a lot of development work, which is not easy. Now back to radar low-frequency dipole antenna. They are flown on board Mars Express, Marsis, and MRO Charade, and not without any problems. Actually, there was some problems on Mars Express. We can see on the right picture the stowed Marsis antenna coming from GPL, which is basically something like 9-limb unsynchronized deployment. It was part of the background because our spacecraft prime, Airbus Toulouse, was the same for Juice and for Mars Express. Now, the animation that most of you know from the various deployment. It's useful to keep this in mind because we will be looking at the configuration of the spacecraft. We obviously start with the solar array, 2 wings. The second wing is deployed shortly after the first one, not at the same time. Gigantic wing with a so-called cross-shaped solar array wing, which is not usual. Then medium gain antenna is deployed to allow the communication with the Earth, and then we start, in principle, the deployment of the RIME antenna in 3 stages. First stage, second stage of the first monopole, and finally third stage. After this third stage, the RIME antenna is deployed. Then we continue with the Mach boom, synchronized deployment at the rear of the spacecraft. Then we continue with the RWI antenna, a 3-axis dipole antenna. And we finish by 4 identical booms located at 4 different locations in the spacecraft. So it was supposed to run like this. It did not happen like this. Now we will concentrate on what we call the nadir deck of the spacecraft, which is the top, where we have the deployed RIME radar antenna. We have also several units like the scientific camera, the navigation camera, the Gala laser altimeter, and several other units. And we have also two monitoring cameras, Juice monitoring camera 1 in the shadow, and this one, Juice monitoring camera, looking in the MX direction, which will be looking towards the sun. What we can say is that we have the view of the GMC2 after deployment. So when the antenna is deployed, we can see other units behind the radar antenna. Now we have a view of the Juice spacecraft in the ESMC chamber in Airbus Astrolab Toulouse. We see first the big high-gain antenna, which is acting as a thermal shield. It means that the sun will come from this direction. The spacecraft is mostly protected by this high-gain antenna. And we have our radar antenna, the EQM model, which has been mated to the spacecraft, which is in deployed configuration, but supported by a lot of white non-conductive pole. It's supported because this antenna does not withstand the gravity itself when it is deployed. So this radar antenna has been designed by STI in Germany with a subcontractor Carbon Space Tech, also in Germany, providing the CFRP booms, LKI and Frentech in Czech Republic, providing the detailed design of the hold-on release mechanisms, providing manufacturing of mechanical parts and associated MGSE, so all the mechanical ground support equipment, and finally, Technical University Dresden in Germany also for the RF analysis. Important in the configuration, the sun is always coming from the high-gain antenna. It will have some impact, mostly on the thermal side. Now, the RIME antenna, it consists of two monopoles. The two monopoles are forming a dipole. We call them PY-MY with respect to the spacecraft reference frame. And each of the monopole, it consists of 4 segments held by 2 HDRM brackets, and the segments are made from carbon fiber reinforced plastic, including a dual cutout slotted spring. So, strange name, we will have a slide for that. And what is important also is that the deployment is sequential. We proceed step by step. When it is deployed, we have a total length of 16 meters, and the deployed part is only 1.6 kilos, so it's attractive. We also need to say that this assembly is what we call centrosymmetric. It means that when we rotate it by 180 degrees, we got the same configuration. Okay. Does it matter? Yes, because it's a potential source of error. If we rotate, the name of the actuator are changed. So we have to be very careful on the orientation of this antenna on board the spacecraft. So, step by step, from stowed to deployed, we will have 2 actuators for the first stage. For one monopole, a third actuator, NEA4, and finally NEA5 to fully deploy this first monopole. Now we will focus on several components out of this antenna, and we'll start with the hold-on release mechanisms, which include hold-on release actuator, 48 on board Juice, which is already a big number, and the record is James Webb, 178 HDRM actuator, all of them single point of failure. So how does it work? This is the NEA, non-explosive actuator. It's not exactly necessarily this kinematic we add on board, but it explains well.
One type of non-explosive HDRM is the split spool initiator. In this design, a groove is carved into the middle of a cylinder. The cylinder is split in half lengthwise, but is then held together by wrapping a tensile wire around it. One end of this wire is fixed to the frame of the HDRM, and the other is hooked to a link wire. Inside the groove of the cylinder is the plunger pin, which is being pressed into the groove by a spring-loaded attachment. Inside this attachment is the threaded coupling to which the bolt is attached. This coupling is also split lengthwise, but held together by protrusions inside of the attachment. To trigger this HDRM and release the bolt, a high current is passed through the link wire. This causes it to vaporize and release one end of the tensile wire. Now, with only one side held down, the tensile wire unwinds and is unable to hold the two hemispheres of the cylinder together. Under pressure from the spring, the attachment along the plunger pin are now pushed forward, now that the cylinder is no longer blocking the movement of the plunger pin. As a consequence of the attachment moving forward, the protrusions that kept the two halves of the threaded coupling together are now moved forward. This then results in the two halves of the coupling moving apart and releasing the bolt. Just like with the pyrotechnic design, the apparent complexity of this design is related to safety and reliability. Since this design does not contain any chemical reaction, the delay from trigger to release is more consistent. The rest of the mechanism is there to redirect the energy of the spring to make the connection between the bolt and coupling fail cleanly.
So this video has been prepared by the James Webb. At some point they were afraid that if any of the HDRM actuator failed, it's already at the end of the James Webb missions. All of them work fine in Juice, so it's not the issue is not directed to the all-done release actuator itself. Now we will move to the hinge itself. It's a monolithic design obtained from a specific machining in the CFRP tube, what we call the dual cutout slotted C-spring. It's an old concept, but barely used. There is also no monitoring means in the hinge. You don't know if it is stowed or open, and you have no easy way to know this. So let's see one of the first video I took myself in 2017 when the first breadboard in STI was starting to work. We are stowed, or folded if you prefer, and we will slowly start to deploy. The moving part of the boom is supported by two helium balloons, that we will soon see. You have two helium balloons which maintain the movable parts in the deployment plane, basically. And we keep opening. We will have at some point some secondary buckling in the CFRP. So everything here is very related to the shape of the cutout. If you have a defect in such a hinge, it influences the behavior. We keep opening, and we start to see some secondary buckling. Final buckling, released, latched. So nice, in one part you do everything. But in this slide there is a but, an English but in red. There is two limitations with such a test. The first one is that the boom obviously stays in the deployment plane because the moving part is in equilibrium with the helium balloon. So you cannot see what could happen out of plane. And the helium balloon are providing a drag effect, which means that this deployment is occurring, as you see in this video, much slower than in the reality without the drag. Finally, there is another constraint. We have seen that this stowed antenna point to the sun. Half of our stowed hinge are seeing the sun, and we will discover over the development that the sun impinging the stowed hinge or degrading the property. So that pushes us to try to deploy this antenna as soon as possible after launch because of this degradation. So the way to approach and try to understand what will happen without the drag is to invest in modeling, what we call multi-body simulation. So on your left, you see what we have been seeing on the video, the final stage of the deployment. We go faster, easily 2-3 times faster than on ground. So, okay, easy. And we will latch, but it's not the end of the story. Under the latching event, a hinge which was already deployed backdrive, and the tip is going downwards, the tip of the antenna. Downwards we have the spacecraft. On one side the Huygens antenna, on the other side some scientific instrument. Okay, so the Huygens antenna is a sturdy stuff, it should be okay. On the other side, well, we have a NASA provided instrument. Can we take the risk to have a diplomatic incident with NASA? We will end up to put a bumper to protect the American instrument. For some reasons that I will a bit explain later, we have also looked at a contingency case. What happens if we deploy 2 limbs at the same time? So this was done in the second step in 21. So we are releasing 2 segments at the same time, intermediate and final are opening at the same time, and obviously the kinematic is different because we have an exchange of stiffness, and we have a backdrive of the middle hinge, then it's going up, then the middle hinge will latch again, second middle hinge latched. At that point we have almost no speed, so we're going slowly to the final position, and because we are going slowly to the final position with a slower speed on the left case, there will be no further backdrive. So overall, this contingency case is not too bad because we are far from having a collisions. Okay, but it's not the nominal deployment. The only drawback is that it lasts, as predicted in this simulation, more than 2 minutes. It starts to be long for the AOCS. The attitude on orbit control systems of the spacecraft is in open loop during such kind of deployment, and 2 minutes start to be long. AOCS engineer is not happy. So it's interesting. We keep this in mind for the recovery. Now, slides on the spaghetti syndrome. What is the spaghetti syndrome? It's not because there was several Italians on board this Juice project. It's because of something else. We have no clue how this antenna behaves out of plane. All the simulation, all the deployment on ground assumes we stay in the plane, but it's not sure. We have. It's very difficult to model what can happen out of plane, and if for some reasons we start to plan to have the simultaneous deployment of the 2 monopoles and they go out of plane, we can have this kind of cross situation. This is not an artistic view. It was produced as part of the anomaly to show that basically it's dangerous, and this is a situation where it's not recoverable. So the top priority is to avoid having a simultaneous deployment for the MY and the PY monopole, because we are unable to test, we are unable to simulate. Basically, we are ready for launch. Here, this is the first view by GMC2 during the ascent phase, and we are still happy because we are our RIME antenna in shape, stowed. We see the Earth behind. The GMC view has been colored after receiving its black and white. Second part of the presentation, the RIME antenna deployment in-flight anomaly and the associated operational constraint. So it happens during the near-Earth commissioning phase, day 2 on 17th of April. Everyone is still euphoric after the launch and early orbit phase, which was perfect. And that day we are ready to go, as the first 2 NEA are fired just after noon, and we got from the GMC1 some confirmation that the first part has deployed. 1 hour later, we are ready to go for the second stage of the first monopole, which is NEA 4 nominal side, NEA 4 redundant side are fired. No chance. In the GMC1 picture, first disbelief. Are we sure we have looking at the good picture? Or his colleague will check and check. Yes, nothing happened. So 1 hour later, first the word ARB, Anomaly Review Board, is pronounced for the first time. It's decided to fire again NEA 4 nominal redundant, but no picture change. We are asking the high accuracy accelerometer, which was switched on and recording. We are asking the data and the Italian team to look at them to see if there's been a shock in order to understand if the famous hold-on release actuator has triggered. It's confirmed 1 hour later that the HDRM actuator has worked properly. We have recorded a shock. So at 4 o'clock, basically, I decided myself to invest in some slides for the first ARB, which is planned on the next morning, with a question, okay, what do we do? Because we have a limited observable at that point. Do we continue to fire or not? 2 hours later, I'm ready to send the first set of slides to the ESA project support team, which is still split between ESOC, ESTEC, and Kourou. So I have to handle the time lag between Kourou and Darmstadt. And at that time, okay, better to go to bed. And 1 hour later, I got the first call from the Juice project manager, which is actually a good question, which he has read the slides, obviously, and why should we fire NEA 5 and nothing else? So that's the first time I spoke about the risk to have entanglement due to out-of-plane deployment. What do we know at that time? We know that through GMC1 we have not deployed anything, and we have deployed, because we see it with GMC1, the first segment. So clearly NEA 1 and 2 have worked. The first stage has been successful. We have no means to see what is the status of the other first part of the other monopole. He is behind a stack which is not deployed, but we assume it has been fine as well. The NEA 4, which has failed at minus 85 degrees, which is cold. And we can also say that the first 2 NEA are taking the launch load. There is almost no preload after the 2 first have released, only 2 Newton. And all NEA have been tested in cold on the engineering qualification model. We also know what happened in Airbus Toulouse on ground. And this view is interesting because we have started to deploy on ground the first segment and the second segment by actuating NEA4. And we also see, by the way, the monitoring camera here. So we can have an association without any ambiguity between the name of the telecommand and the status of this semi-deployed configuration. So when you start to doubt, you're happy to get this picture, because everything starts to be questioned at that point. It has been tested on ground on the QM, but with some limitation, of course. The antenna is tilted for 0G compensation in the TVAC chamber, and there is no easy way to test the huge thermal gradient along the antenna. The part seeing the sun is obviously much hotter than the other part, which is looking to the deep space. So we have a thermal gradient of more than 100 degrees. And okay, maybe something is coming from the fact that we have tested this in cold, no gradient, and we have gradient. Maybe we can try to remove the gradient by some sun illumination. Another problem that we know, day 2, is that this antenna is susceptible to twist. So on this view, it's towed, and we have a bit lost the symmetry. It's difficult to see because basically the hinge we have seen in the first video is now protected by SLI, but basically the stowed hinge is tilted in one direction. So what does it happen? What is the consequence? This is the top view. If the hinge is twisted, then this limb is no longer basically aligned. It starts to touch the static part, hold on bracket on this direction, and also on this point. So actually the friction force is sufficient to cancel the motorization force that we have in the hinge. So we know this is a weaker aspect of the project. We have invested a lot, main inspection, including a final one in Kourou, to ensure that this stack is stowed in a symmetric way. So this is the first idea, basically. We know the weakness in the design. Maybe this is happening now. So that will drive a bit the first set of decision during the day 2. 3 o'clock in the morning, I got all the comments from the project support team, including Kourou. Of course, before an important ARB, many people want to twist and influence the decision. So many exchange before the official ARB. That morning, we also start to know that Ariane Espace report that Ariane 5 launch environment is NC, but we have no detail. So it means that we have exceeded the vibration environment promised by Ariane Espace. So it's not nice because we have some primary notch for this antenna, but since we have no detail, we are unable that day to interpret the info coming from Ariane Espace. It just adds to the confusion. Okay. We start the ARB. I am actually the only one to present some slides with a first iteration of the root cause analysis and focusing on the known weakness of the product and the uncountered on-ground anomaly, especially the one related to the twist effect of the stowed hinge. So there are various options. The opinion in this first ARB, most of the people want to wait. Yeah. But we have also a constraint to deploy this antenna during the 7th first day after launch because the CFRP sea springs are susceptible to creep, and we may lose the potential energy if we stay too long in front of the sun with this one. Even if we manage to release later on the hold-on bracket, it may not release due to this additional creep effect. So there is a delicate decision to be taken. Airbus is coming from with the possibility that there might be some icing issue around the hold-on bracket, because one of them is very cold, minus 80 degrees. So basically we decide together with Airbus to do a first slew limited to 45 minutes around the airwire on the spacecraft. And we propose to fire NEA5 because it may solve the limb friction on the bracket. And we know from the modeling, and we have seen it, that the double in-synchronized deployment that would result in firing NEA5 is not risky from our simulation. So at the end of this first telco, ARB telco, both recommendations are accepted. The NEA5 will be fired at the end of a short slew which is used to heat up the engine. This is what we have seen on Twitter. The various evolutions from GMC2. Basically, we can see that NEA5 has worked because the part which is close to the sun, where NEA5 is located, is lifting after NEA5 firing. There has been the Mach boom deployment. There was a hope that the shock resulting from the Mach boom could help, but actually not much. And the first week, extremely tense ambience because the first recovery failed. The first attempt failed. There was, and also we have the RF people which are not happy at all because meanwhile we did a test with the radar transmitter, and it's a disaster because in this configuration the antenna is in short circuit. So not good at all for anyone, by the way. What can we do with in this stage? We move now to the operational constraint. So, as you know, the Juice spacecraft is operated from ESA Darmstadt, and we have to consider several constraints. And the first one is that we have a limited number of ground paths with S-track. We were using a new inertia during the day, and this is planned for 2 weeks. After that, we are no longer using new inertia. Okay, but we have an anomaly. Can we keep using? No. The planning of S-track is decided well in advance. And well, it's normal work in ESOC, but basically they told us, well, we have a Juice platform which is behaving very well. We cannot lose the spacecraft. We have no way to declare a spacecraft emergency. Yes, you have a problem, but you will not have any additional ground paths. And honestly, after double syncing, it does not help to have more visibility of the spacecraft. Basically, the way to go is to try to understand what happened with what we have on ground. The other aspect is that the NECP planning operation, the slew are designed based on ephemerides by the ESOC flight dynamics teams 1 week in advance with the design, the spacecraft uplink. And this requires some anticipation. You cannot just go on the morning, by the way, can we rotate the spacecraft like this? It does not work like that. So it's the normal work in ESOC, but well, we learn as part of the project support team in ESTEC. Several slew can be done to try to heat up the px hold-on bracket. We have a constraint, and basically all the thermal design has been designed to for all units to withstand 45 minutes. And we have other constraints that we will review. And also, after each flow, we have to wait for 24 hours to be sure that the next flow is starting with the same initial thermal boundary conditions. We can also shake with our main engine 400 newtons or the attitude reaction control thruster in an attempt to try to excite resonance of our antenna, but it's not easy. And the problem is that the boom of the mass is very low, which means that when we shake, the reaction force coming from the acceleration is very low. So there's been some tests done on ground by STI, some test simulation done on the multi-body simulation. Nevertheless, several attempts are planned. And it could be helpful if we have only a friction issue. Thermal aspects. The only possible thermal slew or rotation of the spacecraft around Y, and we have several units that are providing some limitations. The first, the Gala laser altimeter, the telescope receiving unit. If we start to tilt, the sun will impede the primary mirror, and with this goldish color, it's no go. We have also this Juice PEP where it's forbidden to get the sun entering in the slits. This is the slew that we are designing. By rotating around Y the spacecraft, the sun can impinge the px bracket, which is on the rear, nominally fully in shadow. And we have also this primary mirror of the SWI instrument, and this one is locked with two launch lock actuators behind this mirror. We don't like to thermally cycle stowed mechanisms, so we will try to convince SWI to unlock as soon as possible the launch lock of this instrument. It was not planned in the beginning, but it's potentially a showstopper. We'll have to convince this team to come earlier than planned, to explain them why it's useful for the neighbor. We managed to convince them. Another question, we still have some stowed appendage. What should we think? Should we think about the stowed long-rear probe boom? They are not designed to be thermally cycles installed. We are out of the qualification perimeter for those boom. We decide to also launch a thermal study for those stowed long-rear probe boom. So there are many activity on the thermal side. Now, shaking the spacecraft, I have introduced, we have a main engine, which is basically air to brake when we arrive in Jupiter. And the deployed configuration has been designed to withstand the acceleration coming from this main engine, but with a given pattern. And Airbus is now coming with the idea to use another pattern to bring more acceleration to the stuck RIME antenna. Does it fit with the capability of the solar array, especially the yoke? Does it fit with the solar array drive mechanisms? So there is a mechanical team working on this. When we rotate or shake or rock this spacecraft around Y, this is rotating, the platform is rotating, but then due to the inertia of the wing, there is some torque going through the solar array drive mechanisms. Do we take the risk to backdrive the solar array drive mechanisms? Well, is it important or not? Well, there is a motor, an electrical motor in this SADAM. If we backdrive it, it will act as a dynamo and will send back some electrical power in the solar array drive electronic, which has not been designed for this. So we should avoid this. When we also rock, we send a huge bending moment in the deployed Mach boom. We need to check that this is okay with the Mach boom team. We have never computed this load case for Mach boom. So there is another team working in assessing where is the limit in the rocking motion for both the SADAM and the Mach boom. What is the status 2 weeks after anomaly? There are many teams working in parallel to address the root cause analysis. The thermal study are running, rerunning all thermal models from the payload, seeking agreement with the other payload, pushing to unlock SWI. The mechanical analysis are also ongoing. What is the behavior of this semi-deployed antenna under a main engine burn, a rocking motion? There is also another team working on the avionic model to try to implement this rocking motion, because it's a pattern with the reaction control thruster which has never been simulated and tested on the avionic model. So overall, end of week 2, it's between 40 and 50 engineers working in parallel. But actually the ambience is much more peaceful for several reasons. First, there is a plan, and this is a plan we have agreed with Airbus Toulouse and STI what to do which day, which allow all engineering team working in parallel to be aligned towards this plan. And in parallel, the root cause has become clear. We understand what's happening, but there is not yet a consensus end of week 2. Week 3, there will be not much happening, simply because it's 1st of May and it's a day off in France, and Toulouse is not around, and we will not do, ESA will not proceed without the spacecraft prime Airbus Toulouse. So now it's time to address the root cause anomaly, work which has been run in parallel. We will enter in the detail of what was wrong. So this is basically the exhaustive list of what can go wrong. Some of them are easy to be discarded, some of them not. NEF4 initiation failure. There is a clear evidence that both nominal and redundant channel are in open circuit, so it's easily discarded day 1. NEF4 failed to retract. There is a clear evidence from the accelerometer that there is a shock, so it's discarded. Next one, after in the hold-on release mechanisms, there is another spring that we will review in detail. It failed. This will be the final root cause. It was spotted at PDR that there was such a risk, but it was only partially corrected, unfortunately. PY intermediate boom stuck by friction with the hold-on bracket. This was the first thought. Possible recovery with NEF firing, but it did not solve, so it discarded at some point. The hinge facing the sun has got some, has started to creep earlier than thought. So we were trying to assess this also with NEF5 firing. We cannot really conclude on this one. The next one, the hinge is damaged during the launch. Maybe, but meanwhile we got more info from Arianespace on their launch environment, and we concluded it's not realistic. ICE impeding release, so this was the topics brought by Airbus Toulouse, because they got some issue in their previous mission Gaia. Discarded after NEF5 firing. Command error, discarded on day 1 because we have end-to-end on-ground sequence which clearly associate the firing to the command. And this is also the case for the harness error. The telecommand stack has been checked many times, it's also discarded. Meanwhile, STI confirms that we can still live with this antenna folded, looking at the sun. The creep is a controversial topic, it's not easy, especially on carbon fiber materials. This is what our assembly presently stuck. STI will invest in a rendering software, starting to use the GMC2 camera, put the view in the 3D Blender software, including the GMC2 lens characteristic. And from this, the rendering software will be used to determine what we cannot see with the picture. So the start of the view of the GMC2 picture is starting there. We see this part towards the sun. This NEF5 has worked properly. And when we compare the picture, we see that there seems to be, all those booms seems to be pivoting around this point. So there should be an issue on this bracket that unfortunately is not seen by any of the camera. So we narrow basically all what we see to the fact that the NEF4 retainer did not open. So we will enter in the detail. What is this? Here is how the all-down release mechanism is working. So on the left side, on the right side, sorry, we have first the NEA, which is liberating this long fastener. We are in this animation alternating the stowed and the deployed configuration. When this central fastener is liberating by a separation spring on this side, the two release brackets, this part and this part, are also able to move, and they are moving because they are pushed by four springs, this one, this one, this one, this one. When this release bracket is translating, is also liberating this pin, two pins on this side, which then free this top that is holding the intermediate limb. So you can see that from the hold-on release actuator down to the release function, there are many parts. So this is supposed to work, assuming it's symmetric. But we have come to the conclusion that the tolerance chain in this assembly has not been very well controlled, and if you start to rotate, one of the two release brackets start to rotate, this pin will start to be jammed. It means it will be in contact with this point and this point. So this is the hardware. The engineering qualification model of this antenna was made available in STI. We have a bracket which is supporting NEA2 for the first stage, NEA4 second stage, finally NEA6 last stage. One idea was, maybe we are losing the symmetry because the harness, which is very cold, minus 85, is sending a twist reaction and then inducing a rotation of the bracket, but it should have been seen during the cold deployment on ground. So, and then we start to see that this NEF4 assembly, also on the EQM, is prone to jamming. There are some configurations where, with rotation of this part, this pin gets jammed, and if this pin is not retracted, this release pin, this release spring will not open. The boom is supposed to be just underneath this release spring. What is important is that we are coming to the conclusion during a STI workshop that that one did not open properly, but we are able to notice that if we are firing the NES6 belonging to the other monopole, it will create a shock that could overcome the friction. So this was tested during STI workshop in week 4. We are totally unable to know if we have exactly the same situation in flight, but at least it gives hope that firing NES6 could overcome the jamming. The anomaly was pursued after successful release. We have been asking on the AQM parts some metrology to the Czech subcontractor. Another problems. Of course, the translation is working if you consider that your 4 springs, which are freeing this, have equal force. So they should have checked that the compressed springs are producing the same force in the spring. No, 20% of difference from one spring to another one. This is the spring in uncompressed. And when you compress it, you start to see that they have designed something where it's almost compressed at full completely, and its diameter is changing, and they have not checked for the clearance of the compressed spring in the hull. So on top of an unequal spring force, it's likely, especially in cold, that this spring is in compressed configuration is touching its hull in the release bracket. And it could be also that we have remounted for flight after refurbishment of the hold-on release actuator in a bad luck combination, because they did not index the parts. So we don't know what we have flown. Conclusion: bad metrology of the assembly, likely not monitored because not properly toleranced. Recovery analysis of the successful release. The best chance is on the D-Day, 12th of May. And during the workshop in STI, basically we also designed the operational slough, which length of the slough. We started with 45 minutes computed, designed for the spacecraft. We ended up with 72 minutes in total. And with such duration of the slough, we have a bracket, which is a shadow, which is reaching the room temperature. So we are trying to cancel the thermoelastic effect in this bracket. This is the best we can hope, because basically we have also seen and discussed that the fact that we have releasing 2 limbs at the same time does not seem to be risky. We don't want to take any risk with the out-of-plane deployment, so will be achieved by firing NES6. The second monopole will still be stowed because NES3 is still locked. So final recovery plan is the best chance, basically, is to fire NES6 at the end of a long slough to reach the room temperature for the brackets being in the shadow. This has happened on the D-Day, 12th of May. Most of you have seen this on Twitter. The GMC-1 showing the stuck deployment of 2 limbs at the same time. So it's not far away compared to what we predicted. Of course, it's a bit blurred because we need to set up in advance the exposition time on the GMC, the Juice monitoring camera. On the GMC-1, we have long exposure time because we are mostly in the shadow. And time for celebration, both in ESOC and in STEC. You cannot see me because I was so afraid of that it will not work. I was the one which was the most pessimistic. After this successful release, we have also designed a slough for the last one. The second monopole, NES3 remains to be fired. And from this one, we have a much nicer view of what will happen by looking at GMC2. And this is what we have. We have a view every 5 seconds. And we later on, during the summer, we have correlated what we could see with GMC2 with our multi-body model as part of the correlation. It does not happen often that we can correlate a multi-body deployment model with a flight experiment. And there are several things to learn out of this. If you look at this picture, the orientation of this part, which corresponds to this limb, it's a bit strange direction to the left. If you compare this to this, you can see that this one is strangely oriented to the right. We have checked again the picture, and we have come to the conclusion that we have an out-of-plane deployment for this one. For the first one, we cannot see because the view angle for GMC1 does not allow for this. So what we have concluded that we have missed an important event between T0 5 seconds and T0 10 seconds, but by correlating with the model, we are sure it has happened, or what we call a forward detached. Some out-of-plane motion have happened, and we are happy to have not taken the risk to try to have a crossing two-state deployment. And we have less energy. We had to correlate this model. The conclusion is that we have less energy, stored energy in the hinge. So possibly we have lost some energy because the hinge were facing the sun since 4 weeks, so the creep effect, or we have dissipated this energy in the twist motion, out of plane motion. We can also look at the gyroscope, or part of the inertial measuring unit on board the spacecraft, and we can compare what happened with the PX monopole and the MX monopole. This is the first monopole. We can see that we have a momentum exchange between the antenna and the platform. So we have a tilt of the platform around X. This is seen by the green curve, the gyro X channel. And then we are exciting the solar array modes. And when we compare this, of course, everything is inverted because we are deploying in opposite direction. We still have in green the tilt of the platform as a result of the momentum exchange, but on top of that, we have a twist of the platform around Z, which confirms that this antenna, this second monopole, has been twisting. And fortunately, by combining our multi-body model with the CAD configuration, we can confirm there's been no collisions. But basically, we have spent a huge effort to try to prevent this problem on ground. It was a fear effect. We have invested in many inspections, and finally it happened. So it's a bit frustrating, okay. But no indication of collision. So we are lucky. We could have been less lucky. For some reasons, this limb could have been first going on the right, then on the left, and on the left we had just underneath the Huygens antenna. So sometimes we need some luck. This is the end of my presentation.
My name is David Monteiro. I was the product assurance manager for Juice, and I would like to add a few comments to the way that we recovered the situation. Even if we did the test before and after the vibration test on ground, we always know that there could be a problem in orbit. It's never repeatable 100%. In the analysis of what the recovery strategy would be, we looked at different theories of what may be causing the problem that we had. We looked at possibly increasing the temperature to see if there was any effect. We did some operations with the spacecraft to see if that would also give us enough force to release. And finally, one of the operations that we checked caused the release, and we were quite ecstatic, as you can imagine. The process of trying to figure out how to release this antenna was quite interesting. We had a camera, and we had various sensors, and we were able to try to find out what is the best strategy without risking a deployment that could be dangerous to the spacecraft. So in conclusion, this is something that we should examine more in other projects to make sure that the strategy is there in the case that a deployment is having problems.